Hi, I'm Mohammad Farazmand from NC State, and I'll talk about data-driven prediction of multi-stable systems when only sparse measurements of the system are available. I would like to emphasize that this talk is mostly about the metric that we use in the sense that I will describe throughout the talk. This work is in collaboration with my student, Brian Chu. The problem of prediction from sparse measurements is widespread in various fields of science. For instance, in weather prediction, in oceanography, in fluid dynamics more generally. Focusing on the application in oceanography, for instance, direct measurements can be made from several sources in oceanography. One of the most prominent ones, however, is the use of buoys or drifters. There are currently about 1,000 drifters in the ocean. However, given the scale of the ocean, these measurements are very sparse. Similar situation happens in turbulent fluid flows where measurements of the velocity field, pressure, other quantities can be made realistically with good resolution only on a 2D slice of the flow, but this 2D slice is still sparse given the three-dimensionality of the flow. The issue therefore arises as follows, that we have continuum models that describe these systems, but we only have sparse measurements. We can't just feed those sparse measurements in the continuum models and predict their evolution in the future time. To make this more concrete, let me explain the setup of the problem in which my talk is based around. So the problem is as follows. We have a state of the system described by function u. It satisfies the partial differential equations where f is a differential operator and some initial condition of the system is supplied, which is denoted by u naught here. U is a function of x and t, x being the spatial variable, which is in the domain omega. T is time, and the image of that function is r. What I'm going to talk about applies to a more general case where the image is Rn, whereby the state is a vector field, but for simplicity, let's only focus on scalar functions u. Now, if you know your initial condition on a sparse grid, at least on a, on a dense grid over omega, then of course you can do the usual thing we do in numerical simulations, discretize your PD and numerically integrate it to find the state of the system at any future time. By the way, I assume throughout this talk that we know this model. This is given to us. We're not trying to discover it. This model is given and we trust it that it's accurate enough. The problem arises, however, in the case where the initial condition is given only from sparse measurements. In other words, u at any time t can be only measured as its locations xi, I going from 1 to m, and m is relatively small in the sense that I cannot just feed it into my numerical integrator and integrate the PD in time. This problem has been recognized for a long time now, and several approaches have been recommended or developed to address this issue. One of the prominent ones are data simulation methods. For instance, 4D VAR is one of these methods. Ensemble Kalman filtering is another example. And they strive to find, given the observations, to find the initial condition that agrees with the model and with the observations, simply put. Usually for high-dimensional systems like PDs, these are pretty expensive to implement. An alternative approach that has got some traction over the last few years is an alternative approach which says, instead of data simulation, create a large library of states of your system. You do these computations offline, store the states, and then once you're given observations, try to find one of the states from the library that you've computed, or a combination of the states in the library, a linear combination usually, that gives you a state which agrees with the observations. There are several people who have contributed to this approach from various aspects. I've listed a few of them here. This list is not meant to be exhaustive by any means. There are many more people who've contributed to this field. What I'll talk about mostly fits into the second framework, matching against precomputed library. People, as I mentioned, develop different approaches for addressing this problem, but most of them, modulo the details of the work, can be summarized into this flowchart, whereby, as I mentioned, you create an offline library of data, which are states of your system. This requires extensive numerical simulations, but you do that offline once. But when measurements in real time come in, you try to combine the library with the measurements and use regression, machine learning, or other techniques in order to reconstruct the state of the system that agrees with these sparse measurements or make predictions about the system. What is important to us for this talk is this block in yellow. So let's focus on that. In order to do that regression or machine learning, typically in this framework, you need a metric that measures the so-called functional distance between two states in the library or the states from the library and the measurements that are available on a sparse grid. The question then arises, there are two questions that arise. One is what metric to use. For instance, if you're given snapshots of a fluid flow in terms of vorticity field, how do you quantify the distance between these two snapshots or these two snapshots? How do you decide whether they're close in some sense or they're far from each other, meaning that they're very different snapshots of the flow? Another, by the way, this issue has been recognized in data science and machine learning community for a long time now. And a famous example of that is the Swiss roll, which is basically data points on a surface that looks like a roll. And if you want to decide what is the distance between a red dot here and a blue dot here, one thing you can do is to look at the Euclidean distance between them. But intuitively, we know that's not right. What we should do is to look at the length of the curve that goes from the red dot all the way to the blue dot, but it's everywhere on the surface. In other words, in a sense, look at the geodesic distance along the surface itself, because the data has an extra level of structure that has to be taken into account. For instance, diffusion distance, diffusion maps and things like that were invented to partly address this question. The problem we have in hand has that problem as well, the metric, the choice of the metric, but also it has another level of complexity on the top, and it's the fact that the observations are sparse, and as a result, the metric we use has to be computable from these sparse measurements. For instance, if you use the usual functional analysis metric, everybody's favorite, the L2 norm, it's not computable from a sparse number of measurements in the spatial domain. The talk today is about addressing these two questions simultaneously. In order to explain this in further detail, let me set up a problem whereby we look at a dynamical system in the same setting that I explained, but it has the property that I assume that the system is multi-stable in the sense that there are coexisting asymptotically stable attractors for the system. These asymptotically attracting stable attractors can be either steady states, periodic orbits, quasi-periodic orbits, or chaotic sets even. They can coexist in the system, and depending on the initial condition, they can go to one of these attractors. In the example that I will show you, it's a multi-stable system where the attractors, they are all steady states, but they're different steady states. This picture is the most complicated case that can occur. So as I said, according to, or depending on the initial condition you take, you go to one of these attractors. Here is a schematic picture of that, whereby the initial conditions in green go to the periodic orbit, in red they go to the steady state, and so on. And this basically is a schematic picture of your pre-computed library of states. In other words, you create a bunch of, numerically create a bunch of initial condition on a dense grid. This is the numerical part. You have the freedom to create these on a dense grid in space. And then you evolve them, decide where they or observe which attractor they converge to, and based on their asymptotic behavior, label them. In other words, these points, they all go to the periodic attractor, therefore they're labeled in green, and so on. Now somebody gives you a new state and asks you to decide without numerical integration which attractor it converges to. Why without numerical integration? Because remember that the states that come in real time are available only from sparse measurements. So we can't really do numerical integrations even if we wanted to. Now these lines that I've drawn are to mark the boundaries between basins of attractions of different attractors. Basins of attractions, of course, can be much more complicated in reality, but this is just a schematic picture. In practice, of course, we don't have these boundaries of basins of attractions. So this is the picture you're really looking at. We just have a bunch of labeled data in your pre-computed library, and then you have sparse observations of a new state, which is the empty circle, and you have to decide based on the available data in the library which attractor this circle converges to. Let's make the problem a little bit more specific even. What the numerical results that I will show you are applied to this reaction-diffusion equation, which is a PDE. It has a diffusion term and it has a reaction term. U is the state of the system defined on a one-dimensional spatial domain from -1 to 1 and time, and it's a scalar function. Then I will use Neumann boundary conditions for this PDE. And W here that appears in the system is a prescribed weight function, which is everywhere positive. Its value is everywhere positive, and it's also defined on the interval -1 to 1. It's, by the way, time independent this way. It is given to us, it's prescribed, and the task is to find the solutions U. Let me mention that if W is everywhere equal to 1, of course you get the usual diffusion term in your system. Also, it is known that if W is everywhere 1, you have 3 equilibria for the system, where U is everywhere 0 or 1/2 or 1, so that the reaction term vanishes. It turns out that the U equal 1/2 is unstable, but U equals 0 and U equal 1 are stable. So asymptotically, you always either converge to the constant function 1 or the constant function 0, no matter what initial condition you start with. To make the problem a little more interesting, however, what we did, we used a different weight function that is plotted here. It's 1 near the boundaries, and it's a smaller value in the middle of the domain. When you use this weight function, it turns out that U equal 1 and U equal 0 are still asymptotically stable attractors, but 2 new attractors also emerge, which are shown in magenta and black. They look like tangent hyperbolic functions. They're not exactly, but they look like them. So that you have 4 asymptotically stable attractors. They're all steady states or equilibria. And depending on the initial condition, you converge to one of these 4. Therefore, the problem is a little more complicated now than the problem if we had put W as a constant equal 1. Here is this slide basically shows the creation of the labeled pre-computed library. So what we do is that we create a lot of initial conditions. We evolve them forward in time because they're on a dense grid. We can numerically integrate the initial conditions and determine which attractor they converge to as time goes to infinity. Here are the initial conditions. Let's say there are m initial conditions. These are the labeled data. The labels tell you whether they go to attractor 2, attractor 4, attractor 3, or 1. So you create a bunch of labels associated to the initial conditions. And now the task is to classify a new initial condition that somebody gives you, um+1, and decide what label you should assign to. In other words, decide asymptotically which attractor it converges to. I would like to emphasize that this new initial condition that you have to classify is only available now from sparse measurements. So you don't have a dense measurement of um+1 in order to use numerical integrators to find the asymptotic behavior. You only have sparse measurements. To do such a classification, you need a measure of distance between states. You need to find a quantity that basically tells you how far away two functions are from each other. As I mentioned, usually people use L2 norm because it's simple and everybody's favorite is L2 norm. But there is no reason to really think that the L2 is better than some other norm like H1 norm or H-1 norm. Some PDEs now have an intrinsic norm that comes with them. For instance, if you look at geodesic equations, they have an intrinsic norm, which is the Riemannian metric, which is induced by the Riemannian metric that comes from the structure of the equations. Also, I will discuss the reaction-diffusion equation that I introduced earlier also has an intrinsic norm that I will discuss that. But often the PDEs, they don't have a particular intrinsic norm that at least is obvious at the first sight. For instance, Navier-Stokes equations, to the best of my knowledge, doesn't have a preferred norm associated with it. The last thing that I will also discuss, which is the main part of this talk, is a third approach that says, try to learn the norm from the data, directly from the data. What we will insist on about this norm that will be learned are two properties. One is that it's consistent with the data, meaning that similarly labeled initial conditions should be close to each other in that norm. And data which have different labels, in other words, different asymptotic behavior, they should be relatively far from each other in that norm. The other thing, as I mentioned, because our data which we have to classify is only available on a sparse grid, this norm has to be computable from sparse measurements. So these two properties, we will insist that they exist in the norm that we will learn. But first thing I want to do before discussing the learning of the norm is to discuss the intrinsic norm and show you that the reaction-diffusion equation actually has an intrinsic norm. To see the intrinsic norm, you have to realize that the reaction-diffusion equation is a gradient flow for the energy functional that is given here, whereby if you take the gradient of the energy functional, the rate of change of your state is minus that gradient. And it turns out that the right-hand side of your PDE is actually the gradient of this functional. However, one tricky thing arises, and it's the definition of the gradient. This is an infinite dimension, so it's not straightforward as in finite dimensions to take partial derivatives and identify gradient. In infinite dimensions, the gradient is defined as a function that satisfies this identity for any perturbation V. On the left, you have the directional derivative of the energy functional I at the point U at direction V, and the gradient is a function that satisfies this identity for any V. Now note that this is an inner product in some function space, and it's very important what kind of inner product you use. If you use this inner product, which is a weighted L2 inner product, in fact, you get the PDE we're interested in. However, if you use an L2 inner product, the usual L2 inner product without W, then you will get the incorrect PDE, a PDE that we're not interested in. We're only interested in this right-hand side. So it's really important that you use the correct inner product to get the PDE that you're trying to work with. As a result, I refer to this inner product as the intrinsic inner product of the PDE itself because it's induced by the structure of the PDE. Of course, any inner product also induces a norm, and the norm associated with this inner product is given here. It's basically the weighted L2 norm with W being the weight. By the way, W is dictated by the PDE itself. W was the prescribed weights that appear in the PDE. Therefore, this PDE has an intrinsic norm and is given here. Now let me go to the last part, which is about learning the norm from data. To describe that, I have to introduce a few elements. First, I define the similar set, which basically says take any two labeled data initial conditions in the precomputed library, and a pair of them is in S, a pair of initial conditions and is in S if they asymptotically converge to the same attractor. This similar set is the ones that converge to different attractors. So it's basically a set of pairs of initial conditions. Now, in order to learn the norm, I can define norms in many, many different ways. But what I will do is to limit the search to a specific class of norms, which are these weighted L2 product norms, where the weight is phi. And phi is the kernel that has to be learned. This is the unknown that has to be learned. I would like to pause here and emphasize that this intrinsic norm that I introduced here also has a weight in it, but this is not an arbitrary weight. This comes from the PDE. In this part that I want to learn the norm, this is in a sense, an arbitrary kernel, which I would like to learn such that the best metric, the optimal metric, is discovered. In order to do that, we solve the following optimization problem. We would like to minimize this expression. For now, let's forget about the term in red, which is the sparsity promoting. I will come back to it in a second. What I would like to minimize, let's focus on the blue part, is the sum of the distance between similarly labeled data. This is a sum over similarly labeled data pairs. I look at their distance, compute them in this weighted inner product norm where phi has to be determined. And I say that, well, if this is small, it means that similarly labeled data are relatively small in this norm. Excuse me, they're relatively close in this norm. Now, if you just want to solve this and put no additional constraints on the optimization problem, you end up with a trivial solution where phi is everywhere 0. As a result, any two states have 0 distance. So it doesn't give you anything interesting. What you want to do is to add an additional constraint that says, well, minimize this with the constraint that the pairs of data that are in the dissimilar set have a distance which is larger than a threshold that you specify. Here the threshold is 1 and seems arbitrary, but actually this optimization problem is very nice in the sense that it has a scale invariance. If you put a constant alpha here instead of 1, then the optimal solution will be alpha squared times phi. I won't go into details of that, but basically what it says is that the choice of the threshold is not relevant. You can put any number and we normalize it to be 1. Of course, you also want phi to be positive so that the norm is positive valued. You don't want negative distances between states. So you have an additional constraint where phi is non-negative. Now let me go back to the sparsity promoting part. As I will show in the examples, if you don't add this term, then you get a kernel phi, which is mostly or everywhere non-zero. As a result, because it's everywhere non-zero, the norm cannot be computed from sparse measurements. So what we do is we add this sparsity promoting penalization for lambda larger than 0. Lambda, by the way, is a free parameter. If you put it equal to 0, there is no sparsity promoting. But for lambda larger than 0, it ensures that phi is not everywhere non-zero. I'll describe in the examples what it exactly means. Before I move on, I would like to give credit to Xing et al., which really designed this optimization problem in 2003, but they did it for finite dimensional data clustering. We extended this to infinite dimensions. Also, they have no sparsity promoting. Their problem doesn't require sparsity promoting. So we added the sparsity promoting penalization to the problem as well. But this work is really inspired by their work. Now, here's are the examples of how these kernels, optimal kernels, look like. If you have no sparsity promoting, as I mentioned, phi is everywhere non-zero and therefore not computable from sparse measurements. Now, if you start increasing lambda, you see that eventually phi becomes very close to 0 in the middle of the domain, and on the boundary, it becomes non-zero. Let's focus on this case where lambda is equal to 0.5. There are a few things to mention about this. Of course, increasing the sparsity parameter, as we see, makes the kernel to concentrate on the boundaries, which in turn kind of automatically identifies the optimal sensor locations. It tells you where you should make measurements in order for your clustering later on to be more accurate. In this special case, it was discovered that the best locations for sensor placement are the boundaries. In general, you don't know a priori sensor locations, but this methodology will just tell you where to put the sensors. But also another thing is that because the kernel becomes 0 almost everywhere except the boundaries, you can take this picture to its logical limit and say that, well, introduce this sparse norm, which I denote by subscript s, where the kernel is phi sub s, where it's basically delta functions at the boundary of your domain. So you don't measure anything in the middle, you only look at the boundary values of your function u. And from that, you can measure the norm, and as a result, measure distances between states. Again, I would like to emphasize that now the sparse metric that has been learned only requires 2-point measurements for it to be evaluated. To summarize, various kinds of norms can be used. One of them is the L2 norm, everybody's favorite. The second one is the intrinsic norm that comes from the reaction-diffusion equation, and it's a weighted L2 norm with a prescribed weight W that appears in the PD. There is a learned norm that if you put lambda equals 0 in the optimization problem is not sparse, and it looks like this. And it's also, the learned norm is a weighted L2 inner product by construction with this weight given in this figure. But also, when you increase the sparsity parameter lambda, you get phi sub s, which was basically the kernel where you replace phi with two delta functions at the boundaries. And this is sparse in the sense that it can be evaluated from 2-point measurements. The algorithm, therefore, is the following. You generate initial conditions, you evolve these initial conditions and see which attractor they converge to, and you label them accordingly. Once you have the labeled data, you can form your similar and dissimilar sets and solve the sparsity promoting optimization problem that I just described. These first three steps are expensive because you need a lot of numerical simulations, you need an optimization problem. However, you do this once offline and you're done. So you push all the computational costs to offline computations. But then there are 2 steps after that. Somebody now makes measurements, sparse measurements, and gives you these measurements of the new state, and you want to classify this new states in terms of its asymptotic behavior. Now, once you've done the first 3 steps, the next 2 steps are simple. You evaluate the distance between the new state and all the pre-computed states and use a clustering algorithm in order to classify the new state. Here are the results we got. We have the L2 norm, as I mentioned, intrinsic norm, and an optimal norm, the blue curve, which is computed from the non-sparse optimal kernel. And then we have the magenta, which is from sparse optimal norm that we have discovered. Let me first focus on the first 3, which are not sparse, and they require information everywhere in the domain, or at least on a dense grid in the domain to be computable. On the horizontal axis, you see the number of labeled data for each steady state. In other words, it tells you how many states there are in your pre-computed library. And on the vertical axis, you have the classification error. How many percentage of the states that we tried to classify were incorrectly classified, in other words. You see that the L2 norm starts at around 14% classification norm for 5 labeled data in the pre-computed library. As the number of labeled data increase, of course, the error decreases to about 7%. So the L2 norm doesn't do too bad. But the intrinsic norm, if you look at the intrinsic norm, it consistently has lower error compared to the L2 norm. And asymptotically, actually, it outperforms all the other norms that we have used. Now, the optimal norm has a similar trend, does almost as good, but I would like to emphasize some funny, interesting feature that for a small number of labeled data in the pre-computed library, actually the optimal norm that we've discovered, the non-sparse version, outperforms the other norms even. But eventually it has a similar performance. Now, as I mentioned, these three norms are not sparse, and therefore they cannot be used for clustering when you have sparse measurements available. The magenta curve is the same story when now you use the optimal norm with sparse measurements, the norm that only required the boundary measurements. So you're using only 2 points information in order to do classification of your data. And you see that, of course, its errors are larger than the other norms. It's to be expected. It's using way less information than the other norms. However, the worst case scenario, it's close to 16% classification error. In other words, close to 94%, always more than 94% of the data that we classified were correctly classified. So with 2-point measurements, we managed to do a pretty good job in prediction of the asymptotic behavior of the system. For comparison, for instance, if we were to do the classification in a random manner, where we assign labels randomly to the data, then we would get 75% error because we have 4 different asymptotic attractors to converge to. So randomly assigning labels would lead to 75% error. So this is pretty good. To conclude, I would like to say again that the goal of this work was to do prediction of spatiotemporal systems when only sparse measurements are available. Any classification reconstruction requires a measure of similarity between different states. And that can be quantified by norm, but the question is, what kind of norm do you use? And that's the question that we set out to answer. We required the norm to have 2 properties that are going to be important. One is that it has to be consistent with observations, meaning that similarly labeled data have to be close in this norm. And it has to be computable from sparse measurements because that's the kind of data that is in practice available. We formulated and solved a sparsely promoting optimization problem to discover this norm, which we required it to be a weighted L2 norm. But anyway, we discovered the proper weight from solving an optimization problem. And I showed you the application to reaction-diffusion equation. 2 important things to mention is that we didn't decide where to make the measurements in the space. The optimization problem informed where to make those measurements. It told us that the boundary points are the optimal points to make the measurements. The optimal sparse norm was computable from 2-point measurements, as I mentioned. And using it, we were able to predict the asymptotic state of the system with accuracy larger than 94%. If you're interested in more details about this work, we will put a preprint of this work very soon, hopefully in the next 2 weeks on arXiv. So if you're interested, keep an eye on it. Thank you very much.